Okay, thank you again for attending today's Quimper Geological Society's lecture. We give thanks to the peoples of First Nations for being great stewards of the land surrounding the Salish Sea. Some people don't know what the name Quimper comes from, and it's actually the name of the peninsula that we call home here in Port Townsend. So the peninsula is the Quimper Peninsula. And I was just reading last night the Tabor 1878 map, and they were referred to the Quimper sandstone on the east side of Marrowstone Island. So the Scow Bay, sometimes we talk about the Scow Bay sandstone. It's actually the Quimper sandstone. Okay, so I have a couple of announcements. The next talk is November 16th. It's in person only, and it will be located here. And it will be Megan Anderson from the Washington Geological Survey. And she will be speaking about new geophysical data that allow us to see the nature of Silesia rock beneath Puget Sound and how these influence the Seattle Fault. January 11th, it will be a Zoom only. Last January, we had snow, inclement weather cancellation, so we're trying to hold some of the winter months as a Zoom possibility or presentation. And so, since Paul Bierman will be coming from Vermont, well, he won't be coming from Vermont, he'll be videoing in from Vermont, and he's going to be using the past to look into a warming future by talking about climate science, environmental history, and stories related to people who study Greenland. He will tell stories from his new book entitled When the Ice is Gone. Please check our website. It gets updated as we get more information about talks as they're progressing. Okay, now I'd like to introduce Harold Tobin. It brings me great happiness to introduce today's speaker. Um, Harold is a professor at the University of Washington and the director of the Pacific Northwest Seismic Network, and he's the state seismologist. Okay, he received his BS in geology and geophysics from Yale University and his PhD from the University of California, Santa Cruz. He's held faculty positions at New Mexico Tech and the University of Wisconsin-Madison, and prior to moving to Seattle in 2018. So Harold is very excited to present to us today. In fact, last May, the Quimper Geological Society webpage received an email from Harold asking if he could present for us in our community. And after telling me a few things about the project, including the fact that he and his students may have been the first to walk on these rocks since the glaciers had melted, I asked if he could present next weekend. He made us wait until today. His first exposure, so when I interview, I talk to the presenters, I ask them things I like to know, like, what was your first exposure to geology? So he had to take a science class when he went to college, and he ended up taking a geology class. And he referred to it as a very inspiring Geology 101 class, and then immediately took a second geology class. So he knew right away that he was going to be a geologist. And then I like to ask folks, what's your favorite thing to teach? Or what is your favorite project that you've worked on? And of course, he responded first to teaching. And he said that he really loves to bring students from textbook learning to real life experience. And he has a natural hazards and disasters class that has a lot of that kind of light bulbs going off. I asked Harold about what his favorite project was, and without letting him answer, I said, it's this project, right? And of course, once he was able to answer, he said that all of the projects he works on are very exciting, but this one is a passion project. It's one that helps him uh, understand more about the other work that he does, but this passion project doesn't come with a lot of funding. So he's going to explain a little bit more about how this project has actually brought him full circle in his career. So today, Harold's talk is titled Fossil Cascadia Megathrust. Whoops. No, we have a different title. I was afraid that was one thing I was going to ask you today. Okay, uncovering the ancient subduction megafaults in the Olympic Mountains. Please provide a warm welcome to our speaker, Harold Tobin.
I really appreciate that. You were definitely taking notes when we talked about all that stuff for that warm introduction. And so you guys might already be thinking, wait a minute, seismologists, geologists, what are you? The answer is kind of yes, a little bit of all of those things. I kind of work on trying to understand the processes of how faults work. Most of my research is in modern subduction zones. And in fact, a lot of it is trying to study the Cascadia subduction faults offshore in the ocean. If you want to hear about that, you're going to have to invite me back again, because what I really want to talk about today is this much more sort of putting my geological hat on project that really is, as you just said, a passion project for me, and something that, as you'll see, has kind of been sitting there in the back of my mind for literally several decades since I was an undergrad, but I've only managed to actually get a chance to do now, which is to try to understand something about whether we can see the exhumed, the exposed for us at the surface of the Earth version of the faults that we of course can't see underwater and deep underneath the crust in the subduction zone setting of Cascadia or any other one around the world today. And there are a few places where these exhumed subduction faults come to the surface around the planet. There are other places like the Franciscan rocks in California, for some of you will know about them, or the Shimanto Belt in Japan, Kodiak Island in Alaska. But there's really a very small list. And it turns out the Olympics are like the only place where the Cascadia subduction zone actually has an exhumed analog, I think, and I'm going to try to show you why, of the fault system onshore. And I get to go to these amazing places, this view that, well, we'll talk about later on, but of the White Glacier, Mount Tom, Mount Olympus region from the west, which almost nobody ever sees this view because it's kind of hard to get to, as it turns out. So before I get any further, I definitely want to say a lot of what I'm showing you is the work of and is inspired a lot by the enthusiasm of a graduate student and postdoc I'm working with. Anna Ledexi is a PhD student working with me now, who I started talking about this question in the Olympics I wanted to work on, and she's like, come on, stop talking, let's go do it. So we started going to do it in 2022. And then Saiwei Chen, who's a postdoctoral researcher, recently finished her PhD at Penn State, and she's working with me now. And they've been the field team with me and done some really amazing work up there. We're all part of this group that my students named the FAST group, Fault Structure, Stress, and Tectonics, in their Earth and Space Sciences department at UW. So you guys know about the Cascadia subduction zone, of course, and the rest of the world, not just here, actually. I was in Wisconsin when that New Yorker article was published. I gave a public talk at a museum in Milwaukee, and everybody wanted to ask me about this article in Milwaukee, Wisconsin, back in 2015 or whenever it came out. But you know that we have this system where the Juan de Fuca plate is slipping underneath North America, and the boundary between the two plates can be kind of separated into a couple of different zones. If you're deep enough where the crust and mantle are hot and under very high pressure, they flow ductily. They don't store up the elastic or frictional strain that builds up the stress towards future earthquakes. That's only in the relatively shallow part where the temperatures are low enough that that kind of elastic stress, or the stress that builds up for earthquakes, and then the frictional slip, which is we'll also call brittle failure, the breakage of the rock along the fault plane. That is what the earthquake is. In between, there's this thing called the ETS zone, which maybe people have heard about, you know, the tremor that's going on underneath your feet right here every so often, including just a month or two ago. But in between is this zone that's the locked patch called the locked seismogenic zone. And that's the potential source for our truly large earthquake and tsunami. And so we want to understand that fault system, but we don't have access to it, right? It's deep underneath the sea, and then it's also several, kilometers deep underneath the bottom of the ocean to get to the actual plate boundary fault. Now, one thing is, I think people probably kind of intuitively think about that, it's the North American crust banging up against the Juan de Fuca oceanic crust that is where the fault is stuck. But in fact, that seismogenic zone mostly underlies the offshore part called the accretionary wedge. That's the sediments that accumulate on top of the ocean plate and then are scraped off of that. And that's kind of illustrated in this and the next slide a little bit. So here's a cross-sectional view of the same thing. Here's this seismogenic zone. It only goes down to about 20 or 30 kilometers deep. And then this area where North America is plowing along and kind of bulldozing off all these sediments, well, it turns out that most of what we know is where the fault is locked is actually the base of that sedimentary pile where it sits on top of the oceanic crust. Over in the Puget Sound, we live over the zone of ductile deformation, not directly over it, but of course the coastal region and offshore is where that fault is. So Cascadia in a map view has the Juan de Fuca plate subducting in the direction of those arrows at about 4 centimeters per year. Not much, just that much. But that's also 40 kilometers in a million years. So that's the same number, 40 millimeters per year, 40 kilometers per million years. So it's moving pretty fast underneath. And all those ridges you see on the seafloor are actually the ridges that represent the sort of the crumpled up sediments of that accretionary wedge. And we often use this analogy, of a wedge forms like the snow in front of a snowplow blade or in front of a bulldozer, and it's just accumulating this stuff and forming all of these thrust faults, these faults that are the thickening that wedge, and that's what we're seeing. Sorry, it's turned around the wrong way. This is the image I had to grab from it. So the front end of the wedge is over here. The bulldozer is, as you'll see, basically in our area at least, the crescent formation and the Siletzia rocks that form the continental margin of crystalline rocks. But in between is this accretionary wedge, and mostly it lies offshore, all up and down through Cascadia. The one place where there's a continuous accretionary wedge all the way from the bottom of the continental slope right up into the land is here on the Olympic Peninsula. And the little triangle is Mount Olympus, and Mount Olympus is sedimentary, metasedimentary rocks that were turbidite, clastic sediments, sandstone and mudstone deposited on the seafloor out here and then added to the continent. And we'll talk about how we know that and why a little bit more. So it's accumulating this large volume of accretionary wedge. It's also, this turns out, sadly for us, the place where the largest patch of stuck fault is for the whole Cascadia, from Vancouver Island in Northern California, the biggest so-called asperity, or place where we expect the most slip, the largest part of the earthquake's release of that strain is actually basically right here. In fact, they coincide. Probably not coincidentally, but that's a different story. So when we look at this simplified version of the geologic map of the region, all the crescent basalts are this stuff in here. We're sitting up here, of course, right now. And most of Olympic National Park in particular, but of the peninsula itself, is made up of this metasedimentary rock, the stacked up remains of millions of years of that plate convergence, so the accretionary wedge. And everything mapped here in green that's west of or south seaward of the Hurricane Ridge Fault and its equivalents all the way around, it's all originally sedimentary rock. There's none of the basalts are there, nothing else. All of it is basically just sandstone and mudstones, and then their metamorphosed equivalent. So in this zone, we want to be able to look at the stuff that was part of that subduction system offshore and say maybe they contain these fossil faults as a way to understand, learn something about earthquake processes from the kind of the forensic evidence geologists can get from actually studying a fault in a lot of detail. Even if it's not the present day active fault, it's the one we can access and then use as an analog for the present day fault. So we'll zoom in on this area for most of this talk, basically right around Mount Olympus and the region around it. And as you'll see, these enticing faults that come out of the old mapping work that was done a long time ago, but in incredible detail and incredible feat of geologic mapping by Roland Tabor and Bill Cady back in the 1970s. I'll have an image of that whole map in just a second, but conceptually speaking, at least, the idea was if all of this stuff is the sedimentary accretionary wedge, then from their work way back in the 70s, they had this concept of it being off-scraped and turning into the accretionary prism. Each one of these is a fault, and it's just sort of a lot like that bulldozer wedge. Our thinking has evolved on how that process works and has been refined, but the basic concept, they were spot on very early. I mean, this is pretty early in the days of plate tectonics, right? By the early 1970s, I think, these concepts were starting to gain enough currency that Tabor in particular was able to interpret his mapping work as the remains of the subduction zone up here. It's really among the first places in the world, along with Japan and Kodiak, where that was recognized at all. So in a kind of a cartoon view, the concept is something like this, that big accretionary wedge formed, and I'll show one with a little more geological, realistic stuff, but this is taken out of Daryl Cowan's book. I heard you had Daryl Cowan recently speaking to you guys, and Daryl's fantastic, colleague of mine. The idea is that the rocks have somehow gotten into the accretionary wedge and been either scraped off at the front, like the bulldozer wedge, which is maybe the more intuitive way of thinking about it, and added to the wedge, or have actually subducted down along with the plate, the lower plate, and then been added at the bottom of the wedge somehow in a process we call underplating, and then jacked back up again. So they would have taken a path something like this: sediments that were near the bottom of the sedimentary pile out in the ocean, slide down underneath the wedge, which actually means they slide down in the footwall side of the plate boundary fault, if you see what I mean. They have to travel down the subduction zone along with the Juan de Fuca plate, and then get added, and I'll show this in a little more detail in a sec, and then start moving upwards while everything's eroding off the top. So this is the land surface today. There's the coastline. Mount Olympus sits here. Everything up here, of course, has been eroded away and is gone, because Mount Olympus has had many kilometers of uplift, and the whole region of the central core of the Olympics. So I'll show this model a little bit more. Leaves the younger rocks exposed at higher elevations, and it turns out, of course, that these rocks are significantly younger than, let's say, the crescent around it on some of the older material that's inboard. So what we end up with is the high Olympic Mountains as the only surface exposure of these deep rocks from the accretionary wedge anywhere in Cascadia. Right down at Cape Mendocino in Northern California, you see a little bit more uplifted, sort of deeper Cascadia subduction zone, but that's really about it. So there's that sort of same conceptual diagram. This was published by Mark Brandon, who worked here in his early days at Yale. I was an undergraduate doing senior thesis project with Mark in the 1980s. And with a little bit more geological reality here, maybe, is just this idea that there's either faults at the front or these sediments, like the star here, and then the stuff that follows along just above oceanic crust, but gets beneath, and at some depth, either shallowly or more deeply, gets kind of stacked up and shuffled in, just sort of like little wedges sliding one underneath another. And so each one has to bite down from one level of the fault to a new level down in the sediments, takes off a little slice, and then another pizza slice is added under that, and another pizza slice under that, and it jacks the whole thing up in that sense. Meanwhile, it's all eroding off the top, lots of glaciers, things are very actively eroding the system. So in fact, there's good evidence that these rocks have made it down to temperatures and metamorphic conditions that's of, as you'll see, 280, 290 degrees centigrade, and probably a depth of something like 15 kilometers. We don't know the depth with huge precision, but between something like 14 and 18 or 20 kilometers depth, and then made it all the way back to the surface. And in not very much time, at least geologically speaking. The depositional age of the rocks is probably about 30 million years or so, and they've made this upward transect from 15 kilometers depth to several kilometers high in the mountains today in something less than about 12 million years. So pretty rapid rate of things being transported. I should have had this one on the screen when I pointed all that stuff out. So they go down the subduction zone 10 to 20 kilometers to 300 degrees C, then they underplate and get jacked back up to the surface. That's the kind of concept. That's what has been hypothesized for how the rocks got to the high Olympics that we see today. I was interested in that question ever since first learning about it in the 1980s. And as I've worked on these accretionary wedge fault systems in Japan and in Costa Rica and in New Zealand and other places around the world, mostly in the offshore, my mind always kept coming back to the Olympics and saying, okay, if all that stuff was underplated, then that stack should preserve basically now dead but fossil versions of the megathrust fault. If the fault is here and a new fault comes in underneath it, then the old fault should be sitting there somewhere. Some piece of it should be sitting there. And the mapping just said it was all accretionary complex and sort of undifferentiated, except as you'll see, Tabor and Katie left us some clues in the map. So it bothered me. Why don't we see, or can we see, those individual faults in the Olympics? And nobody seemed to know the answer as I've talked to people over the years, and I didn't really get a chance to come back. I was here in the 1980s, so yeah, I moved to Seattle in 2018, but this is back in when I was a senior undergrad, working with Brandon up there, and we had to hike our way in up over Dodwell-Rixon Pass, if you know the area near Mount Queets on the east side of the mountains, and we collect a lot of rocks. There's a good old school frame backpack. Don't use those anymore so much. We made it all the way up to, actually, this is on the middle summit of Mount Olympus, and we collected a lot of rocks for the studies that he published over the years, and some of you know those papers really well, I bet. The Brandon Advance work and all that established that uplift story and the exhumation story of the Olympics. So I'm not really here to tell the story because that work was done in the 1990s, and it wasn't really bedrock geology. It wasn't trying to work out the structural geology. It was just using the rocks as a way to measure the uplift through fission tracks and geochemical tracers and things that are in the rocks. What I was interested in was who has done any bedrock geology to understand whether these faults were exposed out there or not in the Olympics, and what was in all of that accretionary complex. And as far as I can tell, and somebody in the room can tell me differently, but for the core rocks high in the Olympics, high up around the Mount Olympus massif itself, I don't think anybody's looked at them in that way since Tabor did, and he stopped mapping in about 1972, so more than 50 years ago. The map was published in 78, but the field work was all done well before then. There's Tabor and Katie's map. Obviously you can't see any detail in this. It's a tour de force, this map. I mean, this map is an unbelievable geological map, I think. The work that went into this, you guys know what the terrain looks like all in this region, and just being able to even put anything on the map at all is just an amazing feat. That's the region of the glaciers, obviously around Olympus there. But they did all this amazing mapping work and put it all together and in this huge two-sheet thing. So we're zeroing in now on this area, again, right around Olympus and just to the west, and trying to understand what some of these units were that they actually put on the map that, again, people haven't really gone back and taken a look at. So if it's the simplified version sitting over here, we're all in this thing called the lower Olympic subduction complex. This is the stuff that has the highest metamorphic grade. It's not high grade. It's still like, for people who know metamorphic geology, it's kind of at, Pompelliite metamorphic facies, maybe just barely to lawsonite. It's all more on the high pressure, low temperature side, and not so much but it's subleucist, all of that kind of stuff. Anyway, so if we zoom in, Tabor and Katie's map is up in here. You can see where Mount Olympus is. This is it's cut off a little bit there, but this is the current Mount Olympus Quad 100K Washington Geological Survey map. All of this mapping work in this region is just transferred from the 1970s map to this 2000s era map. You can even tell because all of the attitudes that are measured are the exact same ones in the exact same places. I don't think anybody did any more field work since Tabor's work up in here. But what Tabor did was mapped onto these boundaries, and didn't really write very much about them in the accompanying paper. In fact, the paper is concentrated on the east side in general, and he describes all field work west of Mount Olympus was reconnaissance only. So actually the 50-year-old field work is still just recon mapping. And it's kind of terra incognita up in here. You can see, they put some boundaries on the map that are clearly just there for, placeholders, right? In even the published version. All of that got transferred onto the modern map. And I was curious about this boundary. I said, okay, what were they trying to show there? It's mapped as a thrust fault. It wraps around some areas that do have outcrops, so some of it's dashed, some of it's not. And it looks like they're saying that it's a little bit lower grade and a little bit higher grade in here and a little bit more sheared. They put these little squiggly lines that you can barely see and that we paid not much attention to actually before the field work on the map, and said that that was pervasively sheared material, and said nothing else about it, literally just that phrase. So I was like, okay, so what is that? All of the Olympics are deformed rocks, but maybe this was a zone of some kind of concentration. My brain said, aha, maybe in our modern way of thinking about that, that will be a shear zone that does represent one of these paleo faults that we're interested in. But the trick, of course, is getting there. We wanted to examine these structures, and we got in and started doing that. I'm trying to remember what's next. Yeah, okay, so a zoom in. So again, Mount Olympus is here. This is the Blue Glacier over here. I'll show you some photos in just a second. Glacier Meadows is up in there, and this is the. And so in 2022, with 2 graduate students, we hiked up the Hoe Trail all the way to Glacier Meadows, and then put on the crampons and ice axes and got up to Snow Dome, which is on the top of the Blue Glacier, right by Mount Olympus. And we examined the rocks around here. We found a little bit of kind of what we expected from the old mapping, some deformed rocks, but not really evidence of a concentrated melange-like shear zone. And that's what is described for almost all of these more green units over in here. And we were interested in making it to this boundary, but as you'll see, we didn't quite get there until a year later. And now we're hoping, actually, this is labeled, we didn't make it in 2024 this summer over here, but we're trying to make it over to the Valhalla range as well, to try to look at this boundary and the rocks that are adjacent to it. And we're going to look at this area around this place called Lakes of the Gods in just a second. So 2022, we hiked in. That's myself and Anna and Peter Lindquist, another grad student at UW. It was a lot of effort to get there. We found, again, some spectacular exposure of rocks. This is up on the sort of north flank of Mount Olympus in here. That's, let's see, that's Mount Tom over there. And these are some deformed, but still stratigraphically coherent enough to recognize bedding, layers and turbidites. You could tell which way was up. Things are complexly folded, lots of fully overturned and isoclinal folding, lots of individual shear zones, but a kind of a disrupted stratigraphy that we call broken formation. So it's deformed. There's lots of veining. There's that's the same photo, and these different units that we could sort of map out. And we see some places where the sandstones are even very dismembered. This was the most deformed place we could find up on the flanks of Mount Olympus, but we'll still call it broken formation and not an actual melange, clear sort of concentrated shear zone or fault zone. Lots of veins. We sampled a lot of material, and we've been looking at them, and microscopic scale, it sort of confirms those same observations. So as we were up there, this is in map view. Here's Mount Olympus West Peak right here. We sampled along these ridges. We sampled around the Snow Dome hut. If you know about that, there's an old hut for glacier studies up in there that we were able to use to stay in. Amazing place, just beautiful spot. And we found, the observations I just told you about. We wanted to cross over here, and the climbing guide says you can go down onto this surface and walk across the glacier over here to Mount Tom. And this is traced on here, that boundary from Tabor and Katie's map. So that could be at least our candidate for one of these paleo fault zones, but we wanted to get over there. Turns out we couldn't get there. We got to this spot right up here by hiking up the glacier. Again, this is crampons and ice axe material. Get to this point where we're supposed to be able to get onto the White Glacier. And we looked down at it, and the drop into the White Glacier was hundreds of feet deeper than it used to be because the glacier is deflating so quickly, actually. And the climbers are now, I didn't know this at the time, reporting the same thing, that getting down on the glacier is a technical climbing feat that used to be just a simple sort of scramble down slope. It's about 500 feet of death-inspiring scree. We were supposed to go over to there. So we looked at it longingly and said we can't get there on that first trip in 2022 where we were hiking. In fact, we got to this point. This is again the White Glacier here. We're looking a little more westerly, but we saw that there were these lakes and all of this exposed bedrock up in here, and that's actually the trace of that fault back behind. we said, aha, that's where we really want to go, is this zone in here, and we have to figure out how to get there. So we didn't make it in 2022, but we pursued, and to my great shock, actually obtained permit from the Park Service to go in by helicopter and do a field season last year. And we spent 3 weeks by helicoptering into this Lakes of the God region right up in here. So there it is, like zoomed in from that vantage point. We could see that we were in the right place from the geologic map, and that there was a lot of rock exposed, but we didn't really know anything else about it. We knew no one who had been in there, no geologist who had seen it or anything. So it was really kind of flying off of just what we could tell from aerial photography and the old maps. But that stuff was pretty prospective. It's this area right in here. That's one of the lakes right there. And so that's the Snow Dome area. And then this is the site that we wanted to get to. That's the Lakes of the Gods. And then this is the Valhalla's area that we haven't been to yet, but we would like to make it to. So again, yeah, I put it in the slide, but I've already said it. Not examined, and somebody tell me if I'm wrong. I really want to know if anybody has heard about any other work in over 50 years, because we would love to pick people's brains. Roland Tabor, by the way, I knew who he was, but I worked in other things, other places offshore for my whole career. So I never really had a reason to reach out to him. And then as we started to think about this, I thought, oh, I really need to meet him. He's been retired from the USGS. Unfortunately, he passed away in 2020, right in the time, at least, of the, I don't think related to, but in the time of the pandemic, and we couldn't go visit or anything like that. So I've never had a chance to actually talk to Roland Tabor, who did, what did somebody say to me at lunchtime, 16 years or something of field mapping in the Olympics. I mean, just the person who knew the most by far about these rocks by orders of magnitude than anybody else. So here's the aerial photography of the Lakes of the Gods area. These are the outlines of the two main lakes up in there. There's a huge, sort of 1,000 to 2,000 feet sort of valley in between there and the Mount Olympus area proper. And it's really kind of guarded, as you could see from that other photo and from this, on all sides by very steep slopes. You could walk into this area, but it's a scramble. And you certainly couldn't stage yourself for 3 weeks of field work with all the food you need and carry the rock samples out and everything else. So that's how we made the argument that we really needed helicopter access. But the other thing you can see is that there's these, interesting linear features in the landscape picked out by the snow pretty well. And we thought, what are those? Are those just some kind of bedding planes? Or are those some kind of trace of fault systems? And it turns out that they, in fact, actually are traces of stuff related to faults. And once we got in there by helicopter in August of 2023, we just immediately, as soon as we landed in the helicopter, were able to get out, start to unload all our stuff, and then look down beneath our feet at the rocks below us. And we knew we were looking at something different from what we had seen at Mount Olympus immediately. This is literally like feet from where that helicopter landed. And you can see my foot in my field Crocs for, yes, I take the Crocs to the field. Great in camp anyway. And everything is already much more deformed in terms of just a jumble of dismembered layering. Now you can still tell that these are sandstone beds in here, but this is just the beginning of the level of deformation that we saw in there. But immediately it was different sort of grade or quality of deformation than we had seen up around Mount Olympus. We're about, I think as the crow flies, we're 2 kilometers from the peak of Mount Olympus or from the Snow Dome hut. We're very close, but there's a lot of terrain in between. And certainly walking from one to the other just turned out to not be possible. We set up a nice camp. We spent 3 weeks. The helicopter pilot left. And when he came back 3 weeks later, we told him, you're the first person we've seen since you left. There was no sign of people. There was no debris of human occupation in our whole field area the whole time. We saw just no signs of people. The Park Service actually asked us to look for any archaeological material, like worked stones or other things. They gave us a little half-day training on how to recognize worked material because they've never done an archaeological survey of the Lakes of the Gods region. And we never saw any. There's a lot of rock around there. I don't know if I would recognize a worked stone chisel or something, but we certainly didn't see any. But it was home for a few weeks of time, and at least some of the time we had weather like this, and it was it was fantastic. it has amazing exposure. We got to work right away, and there's Anna sitting there, and we just had literally about a square mile of almost 100% exposure, which you guys know the Olympic National Park. That is bizarre, right? Everything is either covered in trees and moss and everything, or it's vertical, or it's got a glacier on top of it. This area was probably glaciated. I'm no expert on that. Not historically, but within the last 1,000 years, I'm sure it was glaciated in this cirque that we're sitting in, where the lakes are. But in the meantime, we had access to all of it, and it's an absolutely phenomenal 5-star set of outcrops from my perspective. So this is looking west, and then the photo that I've used as the ad and everything is looking from the other side. Sorry, I'll go back. Whoops, that's not back. So I'm sitting on this hillside over here, looking back at you in this next photo. That's the White Glacier. Mount Olympus is here. That's the West Peak. And Mount Tom is just off the top over here. And those linear gullies that I saw in the air photo are these linear looking, gullies, valleys that are showing up really beautifully in the photograph. And we recognized pretty quickly that we were looking at a belt of these strongly deformed rocks that's at least 500 meters across or so, and cut by these geomorphic features that are also structural features. Every one of them is an individual, and I'll show you the evidence, an individual concentrated fault strand, a brittle fault embedded within this wider melange zone. And that's what we spent our 3 weeks madly mapping out as fast as we could and sampling enough so that we could do some microstructural work and do the laboratory analyses on after the fact. So if we look at the kind of overview of it, I'll tell you a little bit about the structure and why we think it isn't just sort of some garden variety deformed zone or fault, but actually a paleo megathrust, right? A fossil plate boundary fault zone. And to do that, we did a lot of detailed mapping. So here's the two lakes. We'll see a map superimposed on this scale of image. Notice the scale bar over there. And the individual, I'll keep calling them gullies because that's how we kept referring them sort of just very informally. But in fact, fault strands is the way we really are mapping them out. There's about 10 major ones shown in bold here. And then there's lots of sort of linkages and complex ways in which they kind of are braided or anastomosing in structural geologist, jargon, linked to each other. In between is the disrupted melange. I'll show you pictures of rocks of all of these different types spanning this whole zone. We kind of work our way out of the zone, and as you'll see, into basically undeformed, or at least only weakly deformed rocks up in here that are more reminiscent of what's up at Mount Olympus. And then we have a really concentrated zone in the center here. Each one of these individual black lines as a fault strand has sharp, discrete, narrow, and brittle, meaning fractures, veins, actual fault gouge, which is broken up, crushed rock that's in a fault zone. And those are the hallmarks of not slow, gradual, steady, ductile, or we sometimes even say plastic flow, but of either rapid earthquake slip that has to break the rock and moves at coseismic speeds, which means meters per second, or at least there's some argument about whether all brittle rocks are formed fast or you can do slow but still brittle processes. You probably can. So we could have slow deformation that still creates fractures and cracks and things like that. But there's a lot of evidence for why these might be actually coseismic and fast rupture, fast speed of deformation. So we're mixing all that together somehow in this complicated zone. And I'll define what a principal slip surface is in just a minute. So if we just turn that into a map now, we'll look at a few different features of it. The first simple one is just, we had variations in the lithology. Honestly, the lithology to a geologist, to most of you who are interested in rocks in general, is super boring. It is sandstone or it is slaty, originally mudstone. All of it lightly metamorphosed. A lot of it having had a lot of pressure solutions, so it's certainly been modified some. But there's no chunks of limestone, there's no chunks of basalt, there's no serpentinites, any of the other things we think of in some, like in the Franciscan, in some subduction melanges. But that's what's up there. It is a sedimentary wedge of material that has been deformed. They're not andstones, they're sandstones. um, so we mapped out some big, very coarse, very almost uh, extremely thick beds, several meters in thickness of sandstones in some areas, especially concentrated up in here. And then we had ones with finer scale interbeds of sandstone and mudstone that are kind of the hallmark of, deep water marine turbidite deposition for the cognoscenti of those. It's all pretty deformed, so we probably wouldn't really expect to be able to, but certainly we couldn't see any specific unit sequences that we could then recognize either were or were not repeated, really. So that's an unknown aspect of the whole thing across this belt. Superimposed on the lithology, and again, I'll show you pictures in just a second, but I just want to define my terms first. Superimposed on the rock type is the fabric. So this is the structural degree of development of the kind of disruption, block-in matrix, disrupted melange fabric. And that's shown by these symbols here, where basically the closer spaced the little squiggles are, the more disrupted, the less continuous sort of leftover strings of sandstone bed, let's say, are present in the material. And so we interpret that as essentially degree of shear zone formation or degree of that deformation. So here's some photos. This is from our area of sort of relatively lightly deformed. We see mostly sand beds with thin inner beds of the mud rock. And yeah, they're, in most places in the world, you say that's a pretty deformed place, right? There's a lot of structure in there. It's folded. Some of these beds don't look very continuous. But for our field area, this is our lightly deformed stuff. This is broken formation, but not melange, for example, because we can still see original sedimentary bedding, and we could walk around in here, usually tell which way was up, for example, from grading relations in the beds and things like that. And there's another photo of the same kind of stuff. So yeah, primary sedimentary structures were pretty prevalent in the rocks in this lightly deformed material, which mostly ends up being in the north eastern corner of the map area. Then it goes to the next level where now we start to see, okay, those sand beds are being turned into kind of footballs, right? To elongate, or we call them lenses, lentils, phacoids. Phacoids is the term we use when we don't want anyone else to know what we're talking about. More geo jargon, but blobs of the sandstone that were originally beds, but are now really getting broken up by more and more of these fractures that are just through going everywhere throughout them. Next level, the phacoids are just becoming more and more isolated from each other. There's one and many others, and they're just sort of starting to swim in this sea of matrix that's mostly derived from the original finer grain stuff, the mud rocks, and is separating and isolating them. To the next level, where this is, melange in the sense that, or it's a block-in matrix rock, but each of these, I posted this photo on social media and somebody said, that's a beautiful deformed pebble conglomerate. I was like, there are no pebbles in this photo. That's all originally bedded sandstone and mudstone that has been turned into this through shear process. It's not a conglomerate. And the individual bands in between are made of much finer grained material. Some of it is pressure solution remnants, so it's kind of like the way stylolites form. It's the insoluble remnants from pressure solution, but a lot of it is the finely gouged up and broken up material that's turned into finer and finer grained stuff. And there's another photo at the same kind of level of, this is really at our highest grade of formation of the shear zone, and you can just see how much these things are strung out in the melanges. And there is a sort of a little bit more, hopefully you can tell, three-dimensional photo, surface of the outcrop here, and then we're seeing down into it here. And in fact, this very consistent orientation of this foliation, I'll call it, something that looks like bedding but isn't really, it's the shear fabric, was consistent all over the field area very strongly. It's sort of, northwest to southeast orientation, dipping about 70 degrees, 70 to 80 degrees in places, sometimes 60. This is a little bit lower dip maybe. Very prevalent. And in fact, throughout all of this stuff, the foliation orientation stayed pretty much the same everywhere. So these things are individual of these phacoids of sandstone because they're stronger, but in this shearing, flowing matrix of all of this rock. So kind of a diagrammatic view. Anna made this nice diagram, I think, just trying to show you what that looks like. So if these blobs are the sandstones and the foliation is these planar structures here, as things shear, they tend to get elongated or get oriented in the direction where their long axis is parallel to the direction of transport of the shear zone, right? And so they lie in the foliation plane. Again, sorry for the wonky structural geology stuff. I promise not to show many or maybe any more stereo nets after this. One slide worth, but for the people who love them, you know you love them, right? But so in the melange blocks, again, the foliations are really consistent. That's the poles to them. So the plane is, like I said, northwest to southeast and steeply dipping. The fault strands themselves, so the black lines that I had on the map a minute ago, are also in essentially that same orientation. Everything's really parallel to each other, each other, and then the factoids are oriented in a way that plots their long axis over here, which is totally consistent with basically this diagram, that they're that way. So our interpretation, and with some other evidence as well, YPR shears or SC shears, if you like the terminology, we determined that basically the whole thing has the north side going up and transport towards southwest. And the whole fault zone is consistent everywhere that we measured anything with that kind of orientation. So let's see, in the fault strands and the melange blocks, okay. So now I've talked about I just showed you a bunch of pictures of the development of the melange, right? So that is actually, we don't think the melange itself is so much our earthquake structure, and I'll explain why in a minute. It's the fault strands that bound them, and that the melange is caught up the melange is basically all these outcrop blocks, factoids, but on a gigantic scale now of the size of RVs or boats or beyond, tens or hundreds of meters across, these blobs, and they're bounded by these narrow bands of brittle faulting or brittle breakage. And so now I'll talk a little bit about the examples of what this brittle fault zone looks like. Again, 10 major strands surrounded by the melanges, but each fault strand has some specific structures. So if we zoom way in on our most prominent one of them, which is right in here, this band in here is sort of the center, the core of these fault rocks in the Olympics, and we go into that gully zone, then we get in there and we start to look at the rocks in a lot of detail. And we spent days, and actually Anna and Saiwei this year spent a lot more time. I wasn't able to go this year for reasons that are horrible and complicated, and I'm very sad I wasn't up there this summer. But they spent some time, did a lot more sampling, and did a lot more detailed field work, and got some great work done trying to really map out structure. And we laid out tapes on the ground. We did what's called structure from motion by taking literally 1,000 photographs with a camera and then stitching them all together in the computer, and built up a model of just one of these fault zones, actually a couple of different examples in one of these areas. And when we look into the fault zone, then so this is actually the composite orthophotography image that's taken actually from handheld images, but see the scale, it's a lot bigger than a single photo. The boundary of the fault is here where it says wall rock, and then it's very clear this is melange stuff, but not with the brittle faulting. And then there's blobs again, even within the fault zone of those melange blocks, and then in between, and all of the foliations are consistent, but then in between are these fractured up, veined up, and then with actual fault gouge surfaces, individual fault strands. So the discrete faults, we'll call them, they wrap around the blocks of the brittle fault zone, and they have all these consistent fractures. I don't think I'll talk too much about these fracture orientations and what they mean for us, but they're part of the structural analysis that says that this is a brittle fault zone. Here's one photo of one of these strands. This stuff's not the most photogenic in the world, and it tends to be in the bottom of these gullies where there tend to be water flowing, and also we're covered with snow the longest. This is water right down here, you can see. But maybe you can see that this is the wall rock, and it's kind of blocky. And then along this surface right here is a principal slip surface. It's a millimeter wide zone of fault gouge. that has slicken lines in it and other things like that. And it's also got some additional principal slip surfaces wrapping through there, broken bits of vein and rock, country rock, host rock material, all through there. It has all the hallmarks of what we look for when we look at a brittle fault zone exposed along the San Andreas Fault or along lots of other of these fault zones examples around the world. So we think these are the sort of smoking gun of coseismic rupture millions of years in the past. Again, this is not the modern fault. This is an analog to the modern fault that's rupturing through this sedimentary rock that is probably slowly forming the melanges during interseismic periods and then being ripped through by earthquake breakage during coseismic periods. What I mean is that in the 500 years between earthquakes, there's still strain going on. That's the slow process that's doing pressure solution and forming the melange. And then when an earthquake happens, that has a tendency to localize slip into these vanishingly narrow bands. And this is stuff we know from, again, lots of other work around the world. And those narrow bands are what's left behind from coseismic slip, or at least that's the model we're working with at this point. Here's another photo of another one. There's, again, the wall rock boundary. And maybe you can just see that there's a fabric of just innumerable small fractures. And when we sample this stuff, it just comes out as chips, right out of the outcrop like that, because it's got so much fracture material in it and broken up pieces. It really looks very different from the melanges. Okay, how am I doing? I think I'm pretty close to the end of things. I will say that, we sampled the rocks and we wanted to know what their paleo temperature was. What was the temperature at the time of the formation of all these structures? Because maybe they formed very shallowly before it got subducted down. Maybe it never got subducted very far. Or maybe they formed late while it's on its way back up, jacking back up to the surface, right? It's got to ride the elevator all the way from 15 kilometers to the surface of the Earth. But by taking samples of the material that has those structural fabrics and also including the veins and other things, and then using Raman spectroscopy, a tool that can measure basically stuff that started out as carbonaceous material, woody fragments or other biological material, and how far it's gone towards turning into graphite, you can estimate, you can calibrate that for the temperature at the time, the maximum temperature the rocks have ever seen. And well, long story short, all those dots are samples. They're all here. They basically lie in this narrow band, and they tell us that we're right in the temperature range that is expected to be the kind of the heart of the seismogenic zone, the earthquake generating zone, which kind of extends from temperatures of about 150 degrees to about 350 degrees or so, based again on lots of laboratory research on how rocks break and deform and work. So that's been useful and also consistent set of measurements that goes along with the rest of the story. So again, it turns out we're trying still to interpret these rocks, and they have characteristics that match a number of other, the relatively small number of other well-documented paleo-subduction interface faults around the world. There's a great paper by Christy Rowe and others that looked at a bunch of samples taken from different places. Some of them are from the ocean drilling program, Barbados and Nankai. I've actually, a big chunk of my career was working on drilling the core samples that represent some of these data. And then other outcrop places in Japan, in Italy, back to Japan, California, Kodiak Island, Alaska, back to California, that all, and she just represented them as different places down along the subduction interface from the near surface all the way to the lower part of the seismogenic zone. And as a kind of a summary of all of them, they recognize that it's typical to have a melange belt that is several hundred meters in thickness. And that's actually shown over here, total fault thickness of sort of, this is a logarithmic scale, 100 meters to a kilometer, with individual fault strands within it. And that's shown here at the sort of 10-meter scale, similar to ours as well. And then sharp, discrete faults, like those principal slip surfaces I just showed you, down at the sort of centimeter kind of scale, from a millimeter to 10 centimeters in width, again, matching exactly what our observations are for these rocks. So we think we fit well into this global context, and we're finding the first example for the Cascadia subduction zone of something similar, which allows us then to study the kind of conditions under which the faults formed, and surrounded by mostly coherent strata. And so we have all of that in our map. So our working hypothesis, and we're not done, we have more fieldwork planned, that's what I'll end with in just a few minutes, is the plans for the future. But for now, we would say the Lake of the Gods, LOTG, is a paleomagnethrust interface. Anna made this rather dramatic diagram, I'll just call it, with the detachment fault in maybe a previous one, and then a sandwich of the melandrox in between. And we have all of these characteristics that Don Fisher and others recently put together a kind of review paper and said, here are the things you need to have to prove you're a paleomegathrust interface. The block-in matrix or melange-like fabric, that consistent orientation of everything, consistently where you do have relic bedding, that there's sort of a parallelism. So I didn't put this on the slide. Our rocks, I told you, are dipping steeply, 70, 80 degrees, right? We don't think they formed at that orientation because of the relationship to bedding in the less deformed parts and other things. We think they formed at a low angle along the plate interface, along the subduction megathrust, all of that. And then as the underplating process happens, they get either gradually or maybe through one big out of sequence structure cranked up to a much higher angle. So the present day outcrop orientation is not the way they formed. They've been steepened, but that's not atypical. That's pretty normal. So all of this stuff suggests a paleo décollement. Sorry, I didn't use the word décollement before. Some of these slides are straight out of a GSA talk. Paleo subduction megathrust fault zone. That's all that really means for us. And so if we kind of place it into our cartoon-like diagrams, yeah, we'd put it in here and say what we're looking at is a chunk of one of these underplated structures. And I said that at the northwest end of our outcrop area, I should have put our map back up again here, it becomes relatively undeformed. It becomes a more coherent package. And we think that package extends all the way up to Mount Olympus and somewhere beyond. So I don't know where the next boundary is. I'm not even sure if there is one exposed or not as we cross the Olympics, because maybe it's covered by less deeply exhumed rocks. But certainly here, our provisional hypothesis is that we're looking at a system that has some thickness, 500 meters to a kilometer in thickness, and all these paleo megathrust fault examples within it. Here's a version of modern seismic reflection imaging. So this is using acoustic waves, kind of like an ultrasound image of the seafloor off the coast of Oregon, not Washington for this particular image. These are kilometers of depth below the surface of the ocean. So that's, the water is deep, and then there's the bottom of the ocean. Here's the top of the Juan de Fuca Plate's igneous basement. There's 3 kilometers worth of these same kind of clastic turbidite sediments coming in. And over there, we have a structural interpretation of the modern, present day, zero age fault essentially setting, where the fault is hosted in the sediments. And so there are sediments passing underneath the fault, which will eventually make it down, presumably to be underplated somewhere. So the model is that what we're looking at is the preserved remnants of something that started out essentially here, let's just say, in the lower part of this sedimentary section. Doesn't require it to cut down into the lower plate. We don't need any slivers of the Juan de Fuca plate, which some people have objected. You should have that to show that you're a actual plate interface fault. It's not necessary. We know from lots of places around the world that they often express within the sedimentary pile, not just at the base of the sedimentary pile, as the place where the faults are. So the lack of basalt suggests it represents that thing hosted in sediments rather than an igneous basement. And that's been a little bit controversial thing for us to say, but it's turned out to, I think, have some other examples around the world we can touch on. So in a way, we're just getting started. So here I am contemplating this beautiful fault zone that we think we've identified with the transport direction shown by the arrow, all of this stuff, including Mount Olympus itself, thrust over all of this stuff. We have yet to really investigate deeply into, you can see what the terrain looks like. I don't know how we're going to go and actually map across a lot of these rocks at the foot of Mount Tom, but we are going to try to work our way into some of this zone, at least over here, and see where the lower boundary is. We think the concentrated center of the fault is this set of structures right in here, but it's still melange over here, and we've gone down this hillside. We've gone up that way. It's not melange anymore going in this direction. So we kind of know where the top of our fault zone is, but maybe not so well where the bottom of our fault zone is. So the adventure awaits to continue, right? And I had to throw this in just to point out it's not always sunny and beautiful out there. We had more days that look like that, honestly, than the blue sky sunny days, because it's the west side of the Olympic Mountains, right? Yeah. If the weather's bad in Forks, it's a lot worse up there. Let's just put it that way. But we had a great time. We kept smiling, right? We did crossword puzzles once in a while when it was just too white out to even go look at rocks at all. But works in progress on the samples that we have now. Both of them are working really hard on making thin sections, looking at all the microscale structures. I haven't showed you those today just to keep this as a pretty high level talk. And doing a lot of chemical mapping on the scanning electron microscope, work on the veins, and now we're working on isotopic work on the veins to try to understand their temperature and pressure of formation and some other things. What we really want to do is see more of this mustard colored unit from Tabor and Katie's map and see if, I actually think what they called the penetratively sheared zone was them establishing a map of a major structural shear zone boundary in their overall map, even though they never really called it that. But they put this line on the map for a reason, this line, and they never said really why. And they put all of these squiggly patterns on the map for a reason. And now all we've done is looked at that, basically. The Olympics are just so big and so hard to get around in. But down here by the Valhalla Range, there's a great spot where we think we can be in the same rocks. You can see that Roland Tabor spent time there by the number of measurements on the map. You can tell exactly where Roland Tabor went all the time by exactly where there's just little lines of foliations or strikes and dips or whatever on the map. So it's a great guide to where there's worthwhile outcrop to find. But we plan more field work. We interpret their fault as the basal boundary of this whole package. We're going to try to get in over here. We saw it from up by Mount Olympus. And some of these rocks in here, and actually just out of view between this outcrop in the foreground and these outcrops in the background is a saddle. And in that saddle, there's lots and lots of, again, recently glaciated. Actually, on the topo map, you'll see big permanent ice fields. And I can show you aerial photos that have no ice at all in them because they are not ice fields anymore, or not permanent ones. We still only have a field season that lasts from about mid-August to mid-September. I mean, it's incredibly tight before the snow starts to happen and the weather gets too bad, maybe into the beginning of October. And we can't count on snow-free field area before really August 10th or so in any given year. This year we tried to go early and we blew it. We did an overflight in a fixed wing airplane on like July 15th or 20th, and we're like, no, there's too much snow. It's not even worth going up there. We did take a lot of photos, which I meant to put in a few, but of this area, and we think there's great outcrop and great campsites and other things, and we're going to try to do the same thing we did there down here and extend along this. And I really want to actually hike. I don't know if anybody here has hiked the what's it called, the Skyline Ridge Trail, but that also crosses. Yeah, okay, I see some hands. I haven't hiked it. I actually tried when I couldn't helicopter in this year. I thought instead I'll go hiking, and then the weather was really bad, and I just didn't want to get up on that ridge all by myself. But that also crosses this structure, I guess, somewhere off the map just down here. So there's a few other access points, and that's what I'd like to do. It has just been an absolute amazing place to work, and it's also been a pleasure to tell you guys about it today. I'm sorry if I overindulged on time. I get excited and keep talking, but I'm very happy to answer questions, and thanks for your attention. A deeper spot. One hypothesis is that there's hydration alteration of the oceanic crust, the pillow basalt level, the highest bits of the oceanic crust, and some of the basal sediments, and then they start releasing that water as they get to higher temperature, which drives the pore fluid pressure up. And pore water acts as kind of, a lubricant or a pressure pillow. And so the fault jumps to a new position. And it's very common for it to jump down in the section and therefore bite off these slices. It can do the other thing. It can step upwards and bite the bottom of the wedge off and take it down the subduction zone. There's a whole process called subduction erosion that does the opposite of build an accretionary wedge. It erodes from below. But that's not seemingly what's going on here because we're building this giant mountain range. Yeah. Yeah.
Harold, is there reason to think that west of there you would not find paleomega thrust because what's there we have about
Yeah, exactly. The question is west of there, shouldn't there perhaps be more of these paleo megathrusts, and why doesn't the stack just go all the way out to the coast? And I didn't really show it. It's that pattern of how the uplift, and we know this from the Brandon et al. Work, that the most deeply exhumed stuff is in a bullseye right around Mount Olympus, and I actually think maybe controlled even by this structure at the foot of Mount Tom. So that's come up the furthest. The rocks further west are lower metamorphic grade and have been exhumed from not nearly as much depth, and it seems like not as much paleo temperature, although we want to test that with the Raman measurements. So I think, and in some of the papers he wrote a little later on, Brandon thinks everything to the west of this is frontally off scrape. So it's stuff that never got very deep in the subduction zone. It just became part of the wedge and just went along for the ride. It's really the stuff that has to go with the lower plate and then transfer to the upper plate and then come up. And yeah, that's what we think. We don't know it for sure, but that's what we think.
Okay, if you wouldn't mind just stepping a little bit closer back over to the other microphone without getting so.
There we go. Yeah.
Oh, yes. If you wouldn't mind mentioning, there's another video about the Olympics that you just presented.
Yeah. On Tuesday, Wednesday of this past week, I did the Clallam County Economic Development Group or something. I can't remember who sponsors it, but it's Coffee with Colleen. It was just on Zoom at 8 o'clock, but there's a recording online. On YouTube? Okay, yeah. And it was a completely different talk. It had nothing to do with this. I think I showed one slide or two slides picture of this. Instead, what I was talking about was the source of our earthquake hazards in our region, a little bit about the difference between the Nisqually style earthquake, the Cascadia subduction zone earthquake, the crustal faults like the Seattle Saddle Mountain faults, and so on. And we also talked about some work that a different graduate student is doing that I'm super excited about and proud of with the Quileute Tribal School on establishing a seismometer in schools program and a two-way exchange, cultural and scientific exchange between UW undergrads and grad students with high school kids in the Quileute tribe. And we're extending that to the Makah and Nia Bay School this coming year. And we're trying to grow that across tribes all over the place. So anyway, we talked about all of those different things. People are welcome to go look for that on YouTube. If you want to hear about offshore work and all we're doing to map the modern day faults, which is actually my sort of day job, this is, again, a passion project, but my main research and most of my research funding is for our offshore studies of fault zones. I can come back and give you another talk. You can also watch the Nick... Yeah, right. You can also watch the video I made for Nick Zentner at Central Washington, the Nick on the Rocks guy, which I did for their department seminar. So it's pitched at a department seminar technical level, but it's all about the offshore mapping. Yeah.
So, what part of the Olympics are growing the fastest?
Yeah, thanks. What part of the Olympics are growing the fastest was the question. Basically Mount Olympus and just to the immediate west of it, basically where we're at is where it's going up the fastest, and that's both today measured by GPS, right? We have a GPS station at Snow Dome that continuously records, and it's got a vertical displacement of a couple of millimeters per year. Doesn't sound like much, but a year's not a very long time. And also measured by all of the kinds of geological proxies for uplift rate through this exhumation process. How long has it taken rocks to rise from a certain temperature to the surface? And all of them are consistent with each other. that there's sort of a bullseye pattern, and the highest topography, the highest ground is also pretty much where the uplift is the highest. And it drops off pretty quickly in sort of all directions away from there. It's very, very bullseye-like. Yeah.
This has been a really great thing. I'm really interested in how the crystalline basalts and the celestial basalts are related to this. And one of the earlier maps you showed has the I don't know how to describe it, but how there's like a sort of dip in the way in which those accretionary wedges are forming on the west coast of North American plate, and the Olympic range is unique in that whole strand from North Olympic, from the Vancouver Island down to Oregon.
All the way back while you're asking the question, I'll just keep going back.
Okay, great. Yeah. So I guess I'm just really interested in why. I mean, there's been a lot of interesting things about this for me, and if this uplift of these zones, these shear points from or shear pieces from the subduction are being jacked up like that. Why there and not like north? Why not otherwise?
Yeah.
Is it because of the stress of the salts?
Yeah, here we go. This will do it. Yeah. Yeah. Fantastic question. So why here? Why do the Olympic Mountains exist? Maybe that's actually what your question is in a way. And certainly, why is the accretionary wedge only big enough to be exposed here and come to such high topography? The coast ranges, nowhere else is as high as you go to the south in the coast ranges, all the way down till even the Klamaths in California are not as high elevation. And the answer has to do mostly with another piece of the tectonics that maybe we don't hear about as much. So the plates are converging with each other, but North America and Juan de Fuca are not just converging on each other. This whole chunk of North America, relative to even the rest of North America, is being pushed northward. And it's by this oblique angle. So it's coming in at this angle, and it's kind of wrenching what we call the four-arc sliver, four-arc meaning everything west of the Cascade volcanoes, right, is moving northward. And we can see that in the GPS. I kind of wish I had put in a GPS map. And on the other hand, the Rangilia block, what makes up most of Vancouver Island, is this big sort of thickened bit of crustal material. And it's just sitting there. So there's actually a big north-south convergence across the Olympic Peninsula. And there's a gradient in strain. And that's also basically what's driving the existence of things like the Seattle Fault and Southern Whidbey Island and the network of crustal faults. But what's happening is this isn't just being uplifted, it's also being squashed north to south. At least that's the presently really favored model for it. And so the crescent is all part of Silesia, which also underlies the coast, going all the way down to the south here. But there it's been sort of squeezed up and into that horseshoe pattern. And so north-south convergence is popping this stuff up. It's sort of, you can almost think of it as it's extruding it westward to some extent as well. And there are, the Saddle Mountain Fault sits in here, the Lake Creek Fault and Boundary Creek Fault and the Leech River Fault are all strike slip faults on the north side. And so they're the expression of that north-south shortening. And that's why we have the Olympics and don't have that anywhere else. It's amazing. I think the Olympics are just the strangest and coolest mountain range in North America, but I'm a little biased. So yeah.
We have time for one more question. Okay, well, I appreciate the fact that the accretionary wedge was explained to me a long time ago by one important geologists, but this has been very enriching and eye-opening. And thank you very much for coming to Fort Thompson.
Yeah, thanks.